Good afternoon. Welcome to JCSF Support Foundation tutorial class. I redeem my humble self, JS, your physics tutorial teacher. This afternoon, we want to continue with our topic at hand. In our previous class, so we were trying to look into the work exercises under work. We are dealing with work, energy, and power, and we are still under work. And we need to look into different calculations under the work before we can say we are moving. We move into energy. And if I could remember, for those of you that are following us in our previous class, because of the time management, there is this particular work example that we were dealing with when our time elapsed. So, and we've not concluded with the solution, which I would like we should start from there this afternoon before moving to another work examples. Now, the question we were dealing with in our previous class was, it said the amount of work done, the amount of work done by a crane in lifting, lifting a 10,000 kg car, a 10,000 kilogram car is estimated to be 3 millijoule. Is estimated to be 3 mj. So the work done by a crane in lifting a 10,000 kilogram car is estimated to be 3 millijoule. So estimated 3 millijoule. So to what height is the car lifted? Now, to what height? What height is the car lifted? Now, that is the question we were dealing with in our previous class that we couldn't be able to finish. Now, we have to look into it again, so and solve it before moving to another sort of another questions. So we have to take G. Take G is equal to 10 meters per second square. So now with this now, the parameter here, we were given our mass of the car as 10,000 kilograms. Now, work done is given here now as 3 millijoule, and we have to convert this work done, this millijoule to joule. And by doing that, we said, so 3 millijoule is equal to 3 times 1 million. 3 times 1 million. So 1 millijoule is equal to 1 million joule. So 1 millijoule is equal to 1 million joule. Yeah, sorry for the delay. So I try to control the noise. Now, so 3 millijoule, so will be equal to 3 times 1 million So joule, and this is going to give us 3 million joule. So, but we can just leave it in standard form. So, leaving in standard form will be equal to 3 times 10 raised to power 6 joule. Now, the amount of work done by a crane in lifting a 10,000 kilogram car is estimated to be 3 millijoules. Now, our mass is 10,000 kg. Now, work done, remember that work done is equal to so force times distance traveled. So force times distance traveled. So that is our work done. Now, and remember that force is equal to this is equal to force is equal to mass, so times mg. Force is equal to mg, mass and acceleration, but this acceleration under gravity. So the g is equal to 10 meters per second. Force is equal to mg times, so mg times the what? The distance traveled. And the distance traveled. Now, we were given work done. Our work done is 3 millijoules. And this is the same thing as 3 times 10 raised to power 6 joule. So, with this now, the mass of the car is equal to 10,000. The mass of the car is equal to 10,000 kg times, so the what? The acceleration under gravity, which is 10 meters per second square. 10 meters per second square. Now that is the acceleration under gravity. And this will give us 100,000 Newton. What we are finding is the force. Work done is equal to force times distance traveled. Now, and that's what we want to, it is the distance traveled that I want to find. Because the question is, to what height is the car lifted? To what height is the car lifted? So we know that the crane lifted the car, but to what height is the car lifted? It is similar to the distance. Now, our force now is 100,000. But this, we have that work done is equal to force times distance. Now we've gotten to know our force. Our work done is 3 times 10 raised to power 6 joule. Now our force is 100,000 Newton. Now what we want to find out is the distance. Now with this, now what? So let's move on. If work done is equal to force times distance, our work done is equal to 3 times, this is equal to 3 times 10 raised to power 6 is equal to force. Our force is 100,000. Now what we need to do now is to convert, so this force back to the standard form. And this will be 1 times 10 raised to power of 5. So 1 times 10 raised to power of 5. So times, this is our force. This is the same thing as 100,000. 1 times 10 raised to power 5 is the same thing as 100,000, which is our force, times the what? So times the distance. Now with this now, the distance moved, which we were asked to find the question. So which was the height, to what height is the car lifted? Which is distance. The distance moved will be equal to, we can say 3 times 10. The distance is equal to 3 times 10 raised to power 6 all over 1 times 10 raised to power 5. And with this, we can get our final answer. So here now, this we want 10 to power 1. Now 3 times 10 will give us 30. 1 times 10. Three times 10 will give us 30. Or let's just do it directly so that you all can get the clear understanding about it. 10 raised to power 6, 10 times 10 times 10 times 10. So this is going to give us a long calculation. But when we get it done like this, this can give us 100,000, 3 million over 100,000. So 3 million over 100,000. And if you do 3 million, you know, 3 times 10 raised to power 6 standard form is the same as 3 million. So 1 times 10 raised to power 5 is the same as 100,000. So it is just like we are saying 100,000 in 3 million, and this will give us 30. So meaning that the distance moved. So is the 30 meter, it's equal to 30 meter, and that's our final answer. So with this now, we just done with the question that we were trying to solve the other time before our time, before time couldn't permit us. Now let's quickly move into other exercise under the work. Now let's look into this question. Olaide, whose mass is 25 kg? Olaide, whose mass is 25 kg, ran up a flight. Ran up a flight of 25 steps. Of 25 steps. Each 20 centimeter high. Each 20 centimeter high. How much work did Olaide do? How much work did Olaide do? So, how much did Olaide do? We take G is equal to 10 meters per second square. So let's look into this solution together. Now, the question says that Olaide's mass is 25 kg. The mass of Olaide is 25 kg. So, and he ran up a flight of 25 steps. So Olaide ran up a flight of 25 steps. That is, he has to climb a 25 step. So to climb a flight. So each 20 centimeter high. Each step is 20 centimeter high. How much work did Olaide do? That is the simple. Just like let me just like they have a grammatical representation like this. So let's say that this is the height that Olaide climbed. So this is how Olaide climbed. Now this from Each step to other step is 20 centimeter. According to the question, it's 20 centimeter. Now, another step like this is also 20 centimeter. Till that 25 step, and that's what they are trying to explain here. Olade's mass, we know that Olade's mass is 25 kg. So we round up a flight of 25 steps. This step is 25. Starting from here, 1, 2, 3, 25. Now, each 20 centimeter high. 20 centimeter high. Meaning that this 20 centimeter in 25 places. So that is 20 centimeter in 25 places. So how much work did Olaide do? So how much work did Olaide do? Now, let us look into it. So the distance covered, to know the distance covered by Olaide, to know the distance, because we have to know the distance covered by Olaide before we can know the amount of work done by Olaide. To know the distance covered by Olaide is so equal to the 25 step times this centimeter high, because he climbed 25 steps and each step is 25 centimeters. To find the distance covered by Olaide now, that will be that 25 steps times the centimeter. So which is the same thing as 25 so times 20 centimeter. And 25 and 20 centimeter will give us, let's try to look into it. 20, 0 times 5, 0, 0, 2 times 5, 10, 0 remainder 1, 2 times 2, 4 plus 1, 5. Will give us 500. This will give us 500. Now, the distance covered by Olaide is equal to 25 times 20. So, which is equal to 500 centimeters. Now, so we just know the distance covered by Olaide. To convert this centimeter to meter now, to convert this centimeter to meter now. So this will be 500 divided by 100. Now this is equal to 5.0 meter. So this is the distance covered by Olaide. But that is not our final answer. The opposite force, which is the opposite force, which is the Mg. Opposite force of Olaide. Opposite force Mg. You know that force is equal to mass times acceleration under gravity. So which is Mg, and our force, this is equal to the mass of Olaide is 25. That's 25 kg times G, acceleration under gravity, which is what? 10 meters per second square. Now, 25 times 10, this will give us 250 force. Force, the 250 what? Newton. That is the unit of force. Now, opposite force Mg is 25 kilograms times 10 meters times 10 meters per second square, which is equal to 250 Newton. Now, here is the opposite force of the force of Olaide. Now, but don't forget that the question is how much work did Olaide do? And before we can find the work done, we must know the force and we must know the distance. And that is why we have to move through all this. So because the question is work done, and we know that work done is equal to force times what? The distance traveled. Now, so the force, the distance is what we find here as 5 meters. The force is 250 Newton. Now, with this now, we can move forward to find the work done. So by Olaide, we can find the work done by Olaide. And this work done is equal to force times distance. Force times distance. Now this is equal to, so our force is equal to 50 Newton times the distance. Our distance is 5. 5.0 meter. So 5.0 meter. Now 50 times 5 now will give us something. 50 times 5 will give us something. 50 times 5, 5 times 0, 0, 5 times 5, 25. Oh, sorry, that's error. It's not 50. Our force is 250. I was writing 50. So the force is 250 times distance, which is what? 5 meter. 250 Newton times 5 meter. Now we are going to multiply 250 by 5. 5 times 0, 0, 5 times 5, 25. 5 remainder 2, 5 times 2, 10 plus 2, 12. That is 1,250 joule. 1,250 joule. 1,250 joule. Now, and that's our final answer. That's our final answer. If there's any viewer online that need to ask any question, because they can move on to ask the question before we move on to another exercise. Because we have to deal with almost every of the others. I said that any form or any way that the question is being thrown to you, so you can know how to challenge it.
So how did you get the 5?
You said?
How did you get the 5? That's 250 Newton times 5.
How did I get this 5?
Yes.
This 5.0?
Yes.
This is how I got it. Now, we first find the distance covered by Olaide. And you know, Olaide climbed 25 steps. So, and the height of each step is 20 centimeters. Now, that's how we got 25 times 20. 25 times 20 will give us 500 centimeters. Now, the 500 centimeters is the distance covered. This is the distance, but it is in centimeter. We convert it back to meter. That's how we arrive at 5.0 meter. So to convert from centimeter to meter, that will be, you divide by 100. Why to convert from meter to centimeter, you multiply by 100. I hope you understand. Did you get my explanation?
Yes, sir. Okay, sir. Yes, sir. Go ahead. Yes.
Now we can move into another work under work. Then after that, we can now move to energy. We may just explain some little thing about energy. Then we move to the work example of energy in our next class. But let's quickly look into one more example under work to clear our doubts under the work exercises. Now let's look into another example here. A constant force of 40 Newton. A constant force of 40 Newton acting on the body. Acting on the body, initially at rest. Initially at that gives it an acceleration of of 0.1 meter per second square for 4 seconds. For 4 seconds. Calculate the work done by the force. Calculate the work done by the force. Now, there is no any way that we can, according to this question, there is no any way that we can solve this question without putting some equations of motion. Because here I say constant force of 40 Newton. Now, actually, we want to find the work done, but there is no any way we can find a distance here. A constant force of 40 Newton. This is the force acting on the body initially at rest. So acting on the body initially at rest. So here now we have something we call initial velocity, which is u, and this is equal to 0. So u at rest is 0. So acting on initially at rest, give it an acceleration of 0.1 meter square. So our acceleration is equal to 0.1 meter per second squared. Now, for 4 seconds.
Excuse me, sir.
Okay.
Do you, I don't understand. U equals to 0. I don't understand it. How do you do it? I don't understand. I don't understand the acceleration equals to 0.1 meter per square.
I can't get your question.
No, you said U equals to 0 and acceleration equals to 0.1 meter square. This U equals to 0. I don't know how to do it.
Let me try to explain again. Now, looking at the question, it said a constant force of 40 Newton. Our force is 40 Newton, acting on the body. So if force is acting on the body initially at rest, the body is at rest. The body is at rest. So, but the force is trying to act on the body that is at rest. And when the body is at rest, so the initial velocity is equal to 0. That one is under, if you have been following my previous class on that motion, so you will understand and you will have done that. So when you say that when the body is at rest, so its initial velocity is equal to 0. And initial velocity is u. So, and that is why I say u is equal to 0. So because acting on the body initially at rest, so we put this initially at rest. And when the body is initially at rest, so u will be equal to 0. We have to put it out. But when we don't put it out, when we start to be applying the equation of motion, we will need this velocity. Because here now velocity is given already. Because we said that body is at rest. And when the body is at rest, the velocity must be 0. And initial velocity is equal to u, which is what? 0. Now, how we got 0.1 is this. It is given in the question. A body initially at rest. Give it an acceleration of 0.1 meter per second square. And that's how we got this. Our acceleration is equal to 0.1 meter per second square. Are you following? Do you get what I just explained?
Yes, sir. Yes.
Okay. Now, so give it an acceleration of 0.1 meter per second square for 4 seconds. For 4 seconds, that is time. T is equal to 4 seconds. Now, what again is force F, which is equal to 40 Newton. Now, what is here now are the parameters. The parameters given. So remember, we have different equations of motion. So we have
G is equal to U plus AT.
Is equal to UT
UC
half
plus half AT squared.
AT squared. Yes, and so this equation of motion can really work for this question, whereby we can just say our U will be what? 0.
0
times T. Our T is 4.
4 plus
half our A acceleration is 0.1.
0.1.
0.1 times our T again is 4. 4 squared. Now this will be equal to 0 times 4 will give us 0 plus, so 4 raised to power 2, let's say half times 0.1 times 4 raised to power 2 will give us 15. So here now we can just, for us not to be confused about the calculation because of this 0.1 because of this 0.1. So we can just say half times 16 times 0.1. And you know, half times 16 will give us 8 times 0.1. Now, what we are trying to find is the distance, and that's why we have to use this formula. We have to get down of first. So we want to find the work done. And you know, work done is equal to force times distance. We know the force is 40, but we don't know the distance. So to get the distance now, that is why we have to use this equation of motion, ut plus half at squared. And that's what we just did now. So half times 16 times 0.1, that is 8 times 0.1. So if we work 8 times 0.1 on our calculator, let me try to press my calculator. Huh?
0.8.
0.8. 0.8 meter. Now, by getting this now, we can now find the work done. We cannot find the work done now. Cannot find the work done. So, and the work done is equal to force times distance. So, yeah, but you cannot say that our force is 40 Newton. 40 Newton times our distance now is 0.8. 0.8. 40 times 0.8, whatever you get will be our final answer. But the answer must be in joule.
That is 32.
Any question? What is the final answer?
32.
32. This is equal to 32 joule. So with this now, we can move to energy. No. I think she's outside. Now, we want to start with energy now. So we want to start with energy. So after energy, we can now move to power. And when we look into energy, so it's the ability to perform work. Before you can perform a work, so you must put some strength, and that is energy. So it is energy. So energy is the ability, so our capability to do the work. So energy is denoted by the symbol E, and it is measured in joule.
Bye.
So now, whichever work we do, so we have to apply energy. Somebody that is trying to carry a block now, I want to lift a block. from the ground up. So the person is trying to perform a work. So I have to apply some energy. So you have to apply some ability or capability before the work can be done. So that is energy is the ability to do work. So let's look into some forms of energy, because these forms of energy are what we'll be dealing with under all sorts of calculation that we come across under energy. So let's talk about the forms of energy. Forms of energy. So we have mechanical energy. We have mechanical energy. Mechanical energy. We have electrical. We have electrical energy. We have electrical energy. We have light energy. We have light energy. We have solar energy. We have elastic potential energy. We have elastic potential energy. We have heat energy. We have heat energy. We have sound energy. We have chemical energy. We have kinetic energy. We have kinetic energy. We have nuclear energy. So we still have some lot more. So, but let's quickly talk. Let's briefly talk about the one listed on the board first, before we move on to another forms of the energy. Now, the first one is the mechanical energy. So a mechanical energy is the energy that is associated with machines at work. So the energy that is associated with machines at work, that is mechanical energy. Now, another one there is electrical energy. So it is energy that is taken by television set and other electrical appliances. That is electrical energy. Now we also have the light energy. Yeah? So the light energy is produced by our light bulbs. So the light bulbs that we use at home, they are being produced by light energy. We have solar energy. It's associated with what? With the sun. Solar energy is associated with the sun. The next one here, we have elastic potential energy. So it is stored in spring or rubber, stretch bows, and catapult. Spring rubbers, so anything that deal with elasticity, that is elastic potential energy. It may be string, it may be rubber, or catapult. So that is potential elastic potential energy. Now another one is heat energy. So heat energy flows from one point to another as a result of temperature differences between the points. So it flows from one point to another as a result of temperature differences between the points. So temperature differences bring about heat energy. Now, another one is sound energy. So sound energy is produced by vibrating objects. So they are produced by vibrating objects. So e.g., so our violins, guitars, so pianos, drums, they are the one that produces sound energy. So what about chemical energy? So chemical energy is stored in food and other fuels. Chemical energy are stored in food.
Hello,
and
Joshua.
other fuel. Yeah.
You have like 9 minutes more.
Okay. So, kinetic energy. Kinetic energy is associated with motion. So it's associated with motion. And we have nuclear energy. So nuclear energy, it is stored in the nucleus of atom. So nuclear energy is stored in the nucleus of atoms. So the rest energy that we will also look into, we have gravitational potential energy. Gravitational potential energy, it is associated with the height above the ground. So gravitational potential energy is associated with height above the ground. Any height that's above the ground is associated with gravitational potential energy. Now we also have magnetic energy. So magnetic energy is associated with what? Magnetism. So it's associated with magnetism. And finally, we have rest energy. So rest energy. Rest energy is associated with rest mass of an object. So with rest mass of an object. Now, those are the forms of energy that we want, that we have, and it is them that we'll be looking into in as we move to when we get to the calculations under energy. Because the question will come in different forms. It may come in the form of mechanical energy, in form of electrical energy, in form of light, solar, elastic potential energy. But it will come in forms of any forms of energy. Now, those are the forms of energy. Now we can move to the sources of energy. So I will do some introduction about it, explain what you need to know about energy. Even if we couldn't be able to move with the calculation of energy because of our time, because we're having less than 7 minutes now. So we will go into the calculations in our next class. But let's firstly look into the sources of energy. Let's look at the sources of energy. So sources of energy. Sources of energy. Sources of energy. So what can give us energy? That is what we refer to as the sources. So something must bring about energy. Because we've already explained energy as the ability to do or perform work. So, and when you have the ability to do work, to do something, so something must give you that ability. So without something strengthening or giving you ability, so there's no way you can do work. There's no way energy could take place. Now, the first source of energy that we talk about here is carbohydrates. So a carbohydrate used for man's numerous activities. So carbohydrate used for man's numerous activities. So a carbohydrate is one of a source of energy. We all know those foods that can give us the carbohydrate, like rice, cassava, yam. Let me just put it as the three crops. So they are the ones that can give us carbohydrate. And when you are taking them, so you will have energy. So that is one source of energy. Let's look into another sources of energy. So energy is acquired from the sun. Energy is acquired is acquired from the sun, especially during the day. Especially during the day. So aside from carbohydrate that can give us energy, so the sun also gives us energy. So we can acquire energy from the sun. So during the sunrise, during the day. So the sun also gives us energy. So, and the last one is the burning of fuels. Burning of fuels. So when we talk about burning of fuels, what are the examples of fuel we are talking about here? So we're talking about coal, talking about oils and gases. Oil and gases. So release in the form of heat to drive steam. Release in the form of heat to drive steam, turbines. So an internal combustion engine. An internal combustion engines. Now, when we talk about sources of energy, now we talk about carbohydrates, So it is the living organism that can receive carbohydrate as a source of energy. Also, the acquired of sun, so this can also be the sources of energy for living organisms. But when we talk about burning of fuels, e.g. coal, oils, so burning of fuels is not applicable, but for man. So burning of fuel, e.g. coal, oils, and gases released in the form of heat to drive steam turbines and internal combustion engine. Now, all these things are needed by the engine before they can work. So this is given before an engine can work. Like somebody that have a motor now. So before you can drive your motor, you must have an oil, so in the engine, and also have a petrol in the tank. So this one we give ability to the car to move. So from one place to another. Now, the fuel now and the oil that is put inside the car is the sources of energy of the car. So that is that about the sources of energy. In our next class, we'll be talking about the derivation of kinetic energy. So we look into the formulas, then we move to the work examples. Then we can now move from there to potential energy and the calculations, so that is under. So with that, we can close for today's class. If there's any question that you need to ask, so concerning what we have explained, you all are free to send your message through my WhatsApp. So I'll be ready for you every time to provide answers to your questions. Thank you once again. My name is Mr. Ankwe Joshua Segbinyon, the physics tutorial master under JCSSF Charity Support Organization. Good afternoon once again. Bye-bye.